Hello and welcome to CPE214 Signals and System. My name is Prom-on. I am the instructor of this course. This is the backup lecture of lecture number 6, Fourier series. In this lecture, we will look at the introduction of Fourier series and the mathematical basis of the method itself and how to use it to process the signals or the system. In this and the subsequent lectures, we will focus on the Fourier series and the Fourier transform. Both methods aim to convert signals and systems from time domain, which has t as an independent variable, to the frequency domain, which have the frequency as the independent variable. So if you imagine the graph of the time or the frequency domains, these independent variables are the x-axis. And what we will focus on the subsequent lecture would be the method itself, the mathematical basis of how can we derive the signals or convert the signal from one domain to another domain, or how can we derive frequency response in this case from the relationship between the input and output. The reasons that we have to learn about the frequency domain beside the time domains or the convolution method that we learned previously is that there are actually many applications that relies on the manipulation of frequency contents of the signals. Here I gave you some examples including equalizers or the communication systems, but if you look around yourself, like the mobile phone, it also contains many applications that use the frequency processing. The basic idea of transformation between time and frequency domain is that you can transform signals and systems in one domain to another domain and vice versa. You can find the application related to the Fourier transform and Fourier series in many places. For example, to create a cochlear implant, one must understand how to separate the speech sound or the voice into separate channels and then activate the right neural. Or the well-known application like Siri or Google Voice, which require the understanding of frequency spectrum in the sense that the speech itself have a multiple frequency that varying with times. Here is an examples of the use of Fourier transform in processing MRI scan. So you can see that it also has its application in that area as well, or processing the geo information data to predict something like earthquakes or predicting the tsunami path or probability. Let's first start by looking at an LTI system. Suppose that this LTI system receives an input e to the s0t, an arbitrary exponential function. What will happen? From the relationship, from the convolution relationship, we have yt equals integrate of from minus infinity to infinity of h tau xt minus tau d tau as a way to process the input and generate the output. So if the input xt minus tau becomes x to e to the s0t, then we would have here as e to the s0t minus tau by replacing the independent variable with t minus tau here. And you can see that e to the s0t minus tau is actually consisting of two terms, e to the s0t and e to the s0 minus tau. And since e to the s0t is not related to the integral variable, we can pull it off to here, e to the s0t, and the inside, the integrate from minus infinite to infinite of h tau, e to the minus s0 tau d tau. This is actually the Fourier transform of the impulse response. We use the capital H to denote this system in the frequency domain. One interesting point about this when you look at the system is that if the input has the frequency of S0, then the output would have the same S0 here. With this system modification modify the input signals, and this system has S0 as an input, which indicates that what it used to multiply the input signal is some function at the value of frequency, the frequency value of S0. Now what will happen if the input consists of three separate terms, A1 e to the S1t, A2 e to the S2t, plus A3 to the e to the S3t. If the input consisting of these three terms, then if we fetch each of these terms into the system separately, we would have the output of the systems equaling to the same input signal multiplying by the system modification at that specific frequency. This is for the frequency S1, and this one is for the frequency S2 corresponding to this, and this is S2 corresponding to the input S2 here, and the response S3 corresponding to the input which has the frequency S3 here, and the output would be the combination of all of these three according to the linearity property. What does that mean? Now let's further assume that the input consists of more than one frequency, that is xt equal the summation for all k of ak e to the skt, multiple frequency. Then the output would be also having multiple frequency with hsk as a scaling function modifying that specific frequency. This also applies to the discrete time signals and systems. So the idea is that if we can decompose the signal into a set of separate frequency components, then we can process the signal of one frequency at a time to calculate the output, which allow us to manipulate the input signals to manipulate in terms of its frequency, and we would be able to do a lot of things from that. Since we are talking about frequency, there has to be certain periodicity in order for the signals or the systems to have certain frequency. So let's first start with discussing about periodic signals. We know that signals is periodic if for some positive value t we have xt equal xt plus capital T. We call this capital T the fundamental period. It has to be the minimum positive non-zero value of t, because you can have 2t which also create the repetition in the signals, but 2t is more than t. Then we have the value omega 0 equals 2 pi over t as the fundamental angular frequency, or fundamental frequency in short. Examples of periodic signals are like xt equal cosine omega 0 t, which is the real sinusoidal signal which having fundamental frequency of omega 0, or xt equals e to the j omega 0 t, which is a complex exponential signal, but this is also periodic signals. Both of these signals have fundamental frequency of omega 0. The higher frequency content of the signal can be described by the harmonic of the fundamental frequency. If the complex exponential signal have the fundamental frequency of omega 0, then we can describe the harmonics of those complex exponential signals by multiplying the integer to the omega 0. Then you have the two, something like 1 omega 0, 2 omega 0, 3 omega 0 to describe the harmonics of the signals, of the periodic signals. Let's look at this right hand side. If you have a DC signals, what you have in the frequency would be you having 1 bar at 0 index, which is something like 0 k equals 0 multiplied by the omega 0, which means that this is frequency of 0. If k equal 1, the first harmonic or the fundamental frequency, if the signal is at the first harmonic, then you would have 1 bar at this k equal 1. If it is in the second harmonic, then you would have the second bar. You would have the bar in the k equal 2. The harmonic describes the multiplicative terms of the fundamental frequency to indicate the higher frequency component in the periodic signals. The basic idea of the Fourier series expansion, or we use Fs here, is to represent any periodic signal with the summation of weighted complex exponential signals at different frequency. When I mentioned it weighted, it means that this complex exponential at this frequency has certain scale ak multiplying with that frequency, and we can reconstruct the actual signal by combining different frequency components together to generate the periodic signals. For example, if the signals look like this, it consists of a large amount of 60 Hz, h equal 1, the k equal 1, and certain small amounts of h equal 3, the third harmonic, and a little bit higher amount at 300 Hz, h equal 5. So when you combine all these together, you will be able to reconstruct original signals. Let's look at some examples here. If the time domain signals, you have a signal with one frequency. Then in the frequency domain signals for the Fourier series, you would have something like these two bars. And let's say that you have another one with a higher frequency, which also has two bars. Combining them together will result in the combination of the frequency components of these two signals. The mathematical basis of Fourier series can be simply summarized into these two equations. That is, you can use the synthesis equation to reconstruct the signal xt from the coefficient ak, or you can use the analysis equation to analyze the signal xt to determine the coefficient ak. But actually, they can also be used in other fashions. Let's look at the tips. You can use the synthesis equation to also analyze simple signals like sinusoidal as well, if those sinusoidal can be decomposed into the complex exponential. But if the signals is quite complicated and hard to decompose, for example, a signal like square wave or triangular wave or whatsoever that you cannot decompose into simple sinusoidals or complex exponentials, then you need to use the analysis equation to integrate for the certain period of time to determine the values of ak. Let's look at the first example. Suppose that you have a simple signal xt equals sine omega 0 t. This sine omega 0 t can be decomposed based on the Euler relation into e to the j omega 0 t minus e to the minus j omega 0 t over j2, which equals 1 over j2 e to the j omega 0 t minus 1 over j2 e to the minus j omega 0 t. If we compare these two terms to the synthesis equation, summation of k from minus infinity to infinity ak e to the j k omega 0 t, then we will see that here k is equaling to 1, and for this one this is minus, so k equaling to minus 1, and this means that the value here would be a1 and the value here would be a minus 1. This indicates that a1 equal to 1 over j2 and a minus 1 equal 1 over minus 1 over j2, and ak for other coefficients would be 0 if they are not equaling to 1 or minus 1, since there are only two terms. But if the signal is not a simple sinusoidal, for example, if the signal is the square wave function that is 0 for a period of time from minus pi to 0 and 1 from 0 to pi, and it repeats with the period of 2 pi. With this kind of signals, we need to use the analysis equation to integrate for the Fourier series coefficients. What we need to do is to first state what we know. We know that the period equals 2 pi. That means the fundamental frequency omega 0 equals 2 pi over t, and since t repeats with the period of 2 pi as well, so omega 0 equals 1. If you do not know how to begin, you can just first write this analysis equation first, and then plug in the values that you know. You know that t here equals 2 pi, and t here consists of two parts. The first part from minus pi to 0, and the second part from 0 to pi of the function fx e to the minus jkx dx, and this one as well, fx e to the minus jkx dx. Because the value of fx from minus pi to 0 is 0, we can then discard this term out and consider only the right hand side terms, which we can substitute the value of fx to 1. We then have the ak equal 1 over 2 pi integrate from 0 to pi of e to the minus jkx dx, and integrate of e to the ax is actually 1 over a e to the ax. So we have here 1 over 2 pi minus jk, and e to the same e to the minus jk pi, substitute the first upper limit, and minus e to the minus jk 0. E to the 0 equals 1 here. So we have ak equals 1 over j2 pi k minus 1 over j2 pi k e to the minus jk pi. This equation is applicable only when k is not 0, because if k equals 0, this would become infinity. So we have to determine another coefficient when k equals 0. If k equals 0, then from the analysis equation, the e to the minus jk omega 0 x would become 1. So this a0 would be only 1 over t integrate for the whole period of fx dx, and actually it is just the area under the curve divided by the period. And if we go back and look at the area under the curve here, is equaling to pi times 1. So this is only pi, and multiplying to the 1 over t, you get a0 equal 1 over 2. These are the Fourier series coefficients of the square wave signals. If we iteratively add more frequency components into the signals, we'll see that the signal would be approximated to the square wave starting from a0, the DC component, and then a1 it would generate this sinusoidal. By starting from adding one component, you would have something like this sinusoidal. Adding another component, you would have a little bit more details, and further you will see that it is the signal has become more or less like the square wave, but it would become the perfect square wave only when you add the infinite number of the frequency components together. You can get the square wave. Now let's talk about the properties of the CTFS. If we have x1 and x2 as two periodic signals with period t, if you can derive ak from xt and bk from yt, then the linearity property is just like the linearity in the earlier lectures. That is, if you multiply the first signal with some scaling constant, and also another signal with another scaling components, and then combine them together, And then if you analyze the frequency components of these two, the linearity properties would state that you would have the coefficient ck, which consisting of the combination of ak and bk with the same scaling values. For time shifting, if the signal xt has the corresponding Fourier series coefficient ak, then if we shift signal by time equal t0, then what we have in the frequency domain would be the same coefficient multiplying with e to the minus jk omega 0 t0. You can look at how to derive this e to the minus jk omega 0 t0 from the textbook. But note that you can see that here t0, the time shift, has been now substituted to the t value here. So this should be some constant values, and these are also some constant value as well. So you can see that this is actually e to the minus j and some constant value. For time reversal, if xt correspond to ak, then if you flip the signal x minus t, what you have is the a minus k, meaning that you would have the same coefficient but in the flipped manners as well. So if the signal is an even signal, meaning that xt equals x minus t, you can see that then ak would equals a minus k as well. But if the signal is odd signals, then you would have the frequency component that reflect the time domain as well. The time scaling, which is an important property for the sampling theorem. If the signal xt correspond to the Fourier series coefficient ak, then if we scale xt by a certain factor alpha, would be reflected in the scaling of the frequency omega 0. This means that you would have the same values of ak, but the fundamental frequency will be changed by the factor of alpha. This is the multiplication properties. If you have two signals, one corresponding to ak, another corresponding to bk, and then you multiply them together, what you have would be something like the convolution of the Fourier series coefficients in the frequency domain. These properties and also the basic mathematical concepts of Fourier series are also applicable to the DT signals. The difference between the CTFS and the DTFS is that when you have the discrete time signals, the number of the frequency components will be limited to the period in the time domain. That is because by having a discrete manners in the time domains, it limits the information contained in the signals, so the information available to transform from the time domain to the frequency domains are only the number of points within one period. This indicates that the maximum number of harmonics that the discrete time signal, the discrete time Fourier transform can have would equals to the total number of points for one period of time. You can use the same tips in the analysis and synthesis of the coefficients for both the continuous time version and the discrete time versions. This is the end of the Fourier series lecture. I know that I cannot cover the detail as I discussed it in the class, but by now you would have already learned about Fourier transform and grasped further concepts underlying the time and frequency domain transformation. So I hope that you would be able to understand the Fourier series better. And the difference between the Fourier series and Fourier transform is only that the Fourier series is applicable only to the periodic signals, while the Fourier transform can be used on either periodic or non-periodic signals. So this is it. See you next time. Bye.